Hi, this is Professor Verkler for ECE 1220 at the University of Utah, and today we are doing lecture 4-4 about combinational logic. Today we are going to learn how to turn real-world scenarios into combinational logic, and combinational logic just means creating a network of gates to represent the output we want. And we're going to learn how to do that given a Boolean expression or given a truth table, how to turn either of those into a network of logic gates. And then finally, we'll talk about multiplexers, decoders, and PLAs, and that may be in a separate video. Okay, so first we'll talk about how to turn a Boolean expression into a logic gate. So let's look at this Boolean expression below. It says A and B and C are true, or A and not B and not C are true. So first, if I were doing a math problem and multiplying these, I would do this multiplication first, this multiplication, and then finally I'd add at the end. So we're going to do the same thing when we're drawing our gates. First, I'll start with a big AND gate over here. And I'll put 3 inputs. That's okay. You can have gates with more than 2 inputs. I'll put a second AND gate here. And then finally, the output of each of those will be ORed. Okay, and now I just have to figure out how to get A, B, C, and A, not B, not C. So if you imagine we have A, B, and C over here, well, that's convenient for this first one because we need A, B, and C for this first one here. But for the second one, we're going to need not B and not C. So I will put a NOT gate going to before B and then the input to the AND. And same with C. C can get a NOT gate and then go to the input of the AND. And then A will just hop on over here. Notice I didn't draw this the most neatly. That's okay. You don't have to be the most neat drawer either. Okay, now what if I have a truth table? So last time I kind of showed you how to look line by line at the truth table at each row and any output that was a logical 1. Then we would write an AND expression for that row, and then we'd OR together all the rows that were 1. That was kind of a method I taught you last class, and its formal name is called sum of products because, right, when you ANDed everything in a row, the AND is a product symbol in mathematics, right, a multiply symbol, and then at the end we ORed them all with the plus symbol. So the sum, because we use the plus symbol for ORs. So that's why it's called sum of products. So let's take a look at this example here. So we circled the 2 lines that had a logical output of 1, and then we look at each of the input values. If they're a 0, we make it a not A, and same with the B, not B. And then if it's a 1, we just leave it as a C, and we AND all those together. So all 3 of those have to be true to output a 1 for this row. That represents this specific row and only that row in the table. And then down here we had a 1 for A and C, and then a 0 for B, so we knotted that B, and so that is an AND expression that represents that specific row in the table and that row only. And then we want to output a 1 whenever any one of those combos is true, so that's why we OR it with the plus there. So the final answer is A, B, C, all those ANDed, or A, not B, C. And when I said A, B, C, technically the not of A and B. Okay, so let's do another example here, what I just showed. Here's a row that has an output of 1. Here's a row, and here's a row. Now I could go and I could brute force this and I could say not A, not B, and C. And for the next row, not A, not B. Oh, sorry, the first one should also be not C. And for the second row, then it would be just a plain old C. And then finally, for this one down here, we'd have A, B knotted because of the zeros, C knotted. And then I could OR all of these together. That's a big, huge expression. But maybe you noticed that I shared the same thing here. Or maybe you noticed over here that these first two cases, there was a big fat 0 here for both A and B, and it didn't really matter what C was, right? Whether C was 0 or C was 1 in this case, it didn't matter. I output a 1 either way. So this part can actually be simplified, right, to just say not A, not B, and not involve the C. And if you had been doing this mathematically, right, you could have done a distribution thing where you pull out the A and the B and you're left with C naught or C. But C naught or C is all possibilities. So that just goes away. So kind of my simplified answer here is not A, not B, or A, not B, not C. Next, we're going to do some real-world examples. And these come from our 3700 textbook, which is the follow-on class to this. So they're talking about a gumball factory that has 3 sensors, 1 for weight and 2 for diameter. So sensor S1 gives a logical 1 if the gumball is too light. S2 gives a logical 1 if the gumball is smaller than the given diameter. And S3 gives a logical 1 if the gumball is larger than a given diameter. And we want to reject gumballs that are too large or both too small and too light. So we're going to turn our English here into a Boolean expression. And then that Boolean expression is something you could turn into a logic gate network. Okay, so too large. What will tell us if it's too large? That's if, let's see, S3, it's a logical 1 if the gumball is larger than a given diameter. So too large, we're going to get S3 as a logical 1, so S3. And then an OR right here, and then it's saying both, and there's an AND, right? So this is going to be ANDed, these two things. So too small. So let's see, S2 is about the smallness, so it'll give us a 1 if smaller than a given diameter. Great, so S2 goes here, and too light. S1 is a logical 1 if the gumball is too light. So and S1. Now, if it had said S1 gives a logical 1 if the gumball is above a certain weight, instead of like under a certain weight like it is in this case, then we could have just done not S1, for example, in this expression. Okay, so now let's make a logic network for this Boolean expression. I'll start over here with the things in the parentheses, which is an AND. And then afterwards, we'll OR that with S3. So we'll start with an AND gate over here. And we're ANDing S1 and S2. And the output of that will be ORed with S3. And our output will tell us whether or not we need to reject the gumball. And you can imagine that logical 1 going and turning on a robotic arm or something. Okay, let's look at another example. So we learned at the end of Unit 3 about switches, and we could use some kind of multi-pole, multi-throw switch to be able to do 3-way smart switches, but maybe it would be easier to use some smart switches. And then we can use digital logic. So I think the important thing about solving this problem is framing the problem correctly so that we can see the solution. So I think I would start with like a mental game in your head of, okay, all the light switches are down, off, which means they're all 0. And when they're all down, the lights should be off. Then I go and I flip one of the light switches on, the lights should be on. So that means in this case, it should be a 1. In this case where I flip just this one on, it should become a 1. Or in this case right here where I flip just this one on, it should become a 1. Now I walk across the room and I flip a different switch and the lights should turn off now, right? They should change state. So that means I have 2 switches up now, but the lights are off. So that'd be like this case right here, or this case right here, or this case right here. And then the final case will be I could walk to the 3rd switch at this point and flip it on. So now all 3 switches are up and the lights were off before, so now I want them to go on. So it turns out that lights should be on whenever there's an odd number of switches flipped up. And the reason phrasing it as light should be on whenever an odd number of switches are flipped up is that might help you make the truth table, or it might help you come up with the simplest gate arrangement. So let us start with the brute force method, and then we'll talk about a simpler gate arrangement. So brute force says whenever there's a 1, I'll AND all these things. So I have S1 knotted, S2 knotted, and S3. Or I can have S1 knotted, S2, and S3 knotted. And for this row here, I have S1 and S2 knotted, S3 knotted, knotted because they're zeros. And finally, I have the last case where it's S1, S2, and S3 are all 1. And then I OR all of these things together. Give you a minute to catch up on that. Okay. So I could write this huge expression that has 3 things ANDed each time and then 4 different things ORed. That is a perfectly valid solution, and you can create a gate system for that. Or a network, I guess I should say. The other thing we could think about is when it's saying that whenever 1 switch is flipped up, that makes me kind of think like an XOR, like an exclusive OR. So you can imagine I have an exclusive OR for S1 and S2. And I will write that over here. So that means that if one or the other is 1, we'll get out a 1. So we'll get a 1 in this case. We'll get a 1 in this case. We'll get a 1 in this case. And we'll get a 1 in this case. Right? Because these are the cases where S1 and S2 only have a single one of them that's 1. And then you could imagine if I ORed that again, or XORed that again with S3, what would happen? So now I'm looking at this XOR over here, XORed with S3. So 0, 0, I'm going to get out a 0. 0, 1, I'm going to get out a 1. 1, 0, I'm going to get out a 1 because there's just a single one. 1, 1, I'm going to get a 0, which is good because I wanted a 0. 1, 0, I'm going to get a 1 again. 1, 1, they're both 1, so I get out a 0. And then 0, 0, they're both 0, so I get out a 0. And then finally, this one is actually a 0, which seemed kind of weird at the time, right? Because I really wanted a 1 out. But now that I'm XORing a 0 and a 1 right here, then it is going to actually give me a 1 out. So this is my like 3-way XOR, you could say, where I chain 2 XORs together. And so now notice that the output exactly matches what I wanted over here.